This week we learned that the universe has a temperature. It's about 2.7 Kelvin, which is just above absolute zero, or 270 degrees Celsius, for those of us who still use Celsius. And this makes sense because we know the universe began with the Big Bang, and anything that starts off hot and is just expanding QAUnt have a temperature below zero. But what does it mean for the universe to have a temperature? How do you assign a temperature to all that stuff, and why should you care? Here's our science news update. The thing about temperature is that it's something we experience. We put our fingers on things and our brains tell us they're cold, warm, hot, whatever. You don't really need to understand how that works. It's basically magic. But there's a mathematical definition that physicists are happy with. When you think of hot objects, you probably think of heat radiation, things like light, or microwaves, or radio waves. The hotter an object, the more energy it radiates per second. So one way of defining temperature is to measure the amount of energy an object radiates per second. For example, the surface of the Sun has a temperature of about 5,800 Kelvin. That means that each square meter of the Sun's surface radiates about 6.3 times 10 to the power 8 watts of energy into space. This definition of temperature only works if the object is radiating energy. If it isn't, then you can't define a temperature for it. So, coming back to the universe, you might think its temperature would be very high, since we see stars and galaxies and quasars and all sorts of bright stuff. However, when scientists want to determine the temperature of the universe, they aren't looking at stars and galaxies. They're looking at something called the cosmic microwave background. This is basically the oldest light in the universe. It comes from a time when the universe was about 400,000 years old. Back then, the universe was still very hot and filled with a hot plasma of protons and neutrons and electrons. Photons were constantly getting absorbed and re-emitted by the plasma particles, so they couldn't travel very far. But as the universe expanded and cooled, the particles eventually started to combine to form neutral hydrogen atoms. At this point, the photons were no longer absorbed and could finally travel through space freely, so they spread out. This is the cosmic microwave background. And it turns out the spectrum of this light fits very neatly with blackbody radiation with a temperature of about 2.7 Kelvin. Blackbody radiation is the type of light emitted by an object when it's in thermal equilibrium, meaning it's emitting and absorbing photons at the same rate. The peak wavelength of blackbody radiation depends on the temperature. Hotter objects radiate shorter wavelengths, so the cosmic microwave background doesn't look like a hot oven, but it also doesn't look like cold outer space. It's just right in the middle. And the reason we think this is actually the temperature of the entire universe is that this radiation is everywhere. It's the same in every direction, and it's the same no matter where we look. In other words, it's not just hot plasma that's emitting this light. All of space is this, includes empty regions with nothing but a few lonely atoms here and there. Even there, we see the same black body spectrum. Physicists love this because it tells them two things. First, the universe is in thermal equilibrium, or at least very close to it. This means that on average, regions that are hotter than others will cool down, and regions that are colder than others will heat up. Second, the fact that the universe has a well-defined temperature means that it's made of normal matter and normal radiation. If the universe had exotic matter in it, like lots of dark matter, for example, then this exotic matter could absorb or interact with the normal stuff in a way that destroys the blackbody spectrum. This is why measurements of the cosmic microwave background are one of the best ways we have of putting limits on the amount of dark matter in the universe. And speaking of dark matter, this week we also learned that experiments searching for dark matter have just entered a new era. Two experiments, Xenon and Pandax, have measured what's called the exclusion limit for the strength of a particle interaction. To explain this, let me first tell you about an idea called the WIMP miracle. WIMP stands for Weakly Interacting Massive Particle. It's basically a type of dark matter particle. These particles would have masses of around 10 to 100 giga-electron-volts, which means they would be heavy enough to be detected with current technology, but also that they would interact with normal matter in a particular way. Specifically, they'd interact via the weak nuclear force and gravity. The weak force is one of the four fundamental forces of nature. The others being electromagnetism, the strong nuclear force, and the large one. It's responsible for radioactive decay, and for some reason it gets lumped together with electromagnetism to make one big group. Gravity, however, is very weak. So the WIMP miracle is the idea that despite being heavy, these particles would be so weakly interacting that they would be very difficult to detect. For example, if dark matter consists of WIMPs, then the best current experiments would only be able to measure a cross-section of about 10 to the minus 48 square meters. This sounds really tiny, and it is, but it is such a small number that it is basically impossible for dark matter particles to bump into protons in detectors. And that's why we haven't found them yet. But that would also mean that they're almost impossible to find. But luckily, we can use a little loophole. Just because dark matter particles don't interact much with normal matter doesn't mean they don't interact at all. For example, they could interact with each other, and that's exactly what Xenon and Pandax have been looking for. They've been looking for the process where two dark matter particles collide and annihilate each other. This can happen if dark matter particles are their own antiparticles. Annihilation would produce two gamma-ray photons that would fly away in opposite directions. Now, it is admittedly a bit hard to see how this helps us, because it seems like just shooting gamma rays into space is going to be really difficult to detect unless you have a gamma ray telescope. But the thing is, the detectors used by Xenon and Pandax are very good at detecting gamma rays. In fact, they were originally designed to look for those hypothetical particles called WIMPs that interact via the weak force. So while you can't aim a gamma ray detector, you can surround yourself with normal matter, which gives the gamma rays a very good chance of interacting before they leave your detector. The new results from these experiments basically say if you wanted to find a particle that interacts like this, you'd have to make it heavier than about 6.3 giga-electron volts. This rules out the so-called WIMP miracle, but it also means that any dark matter particle heavier than that can't be its own antiparticle. These results came out just a few days apart from each other, and they agree with each other and with previous results from other experiments. They also rule out some models of dark matter that were proposed in the 1980s. But most importantly, they now allow other experiments to set better limits on models of dark matter. Basically, the entire field of direct detection experiments for dark matter has entered a new era. If you want to learn more about cosmology or particle physics, check out Brilliant.org. On Brilliant, you find courses on a large variety of topics in science, computer science, and mathematics. All their courses come with interactive visualizations and follow-up questions. Some also have videos for demonstration experiments or executable Python scripts. This really gives you a feeling for what's going on. It's both fun and easy to fit into a busy schedule. Thanks for watching. See you tomorrow.